I'm sorry I couldn't be with you in class today, but I still want to introduce some new material, and it's very much related to what we've been working on. So we've been working on exponential functions. We've been working with logarithmic functions. We've learned how to solve exponential equations. We've learned how to solve logarithmic equations. And now what I want to do is I want to relate what we've learned to the real world. I always say that we don't do math for math's sake, although it seems like we do sometimes. Exponentials and logarithms have some very good real-world applications that we'll discuss. So the first thing that we're going to discuss how people like to model certain behaviors using either an exponential or a logarithm. I'm going to start with exponential growth. So first, I want to take a look here at what it looks like to experience exponential growth. And exponential growth is, well, exactly what it sounds like. Your curve will grow exponentially, like this. And the model that we like to use is y is equal to a times e to the bx, where b is greater than 0. We like to settle in on the natural base, and that way we don't have to worry about selecting base 2 or base 10, or we always use the natural base when we're doing an exponential growth model. Now, what grows like this? Bacteria grow like this. Bacteria like to double, and when they divide, we go from maybe 1 bacteria to 2 to 4 to 8 to 16. So we get this rapid increase here, and that's why infections are such a problem, because even 1 bacteria can multiply and ultimately become a very large population of bacteria. What else grows like this? Companies grow like this. So some companies spend many, many years back here not growing very much. Then all of a sudden something happens. They get some funding, their product becomes a big hit, and then they take off. That's also modeled by exponential growth. I think what I'd like to do, though, I'd like to look at a very specific case, and that would be population growth. So I'm looking at the example in the book, a good example, and it's the population of fruit flies. So it says a research experiment, if you look in the book, a population of fruit flies is increasing according to the law of exponential growth. So the population increase is along this curve somehow, but we just don't know what A and B are. A and B can be any value really, but B does need to be positive to ensure that you get growth. Let's see what it says. After 2 days, there are 100 flies. After 4 days, there are 300 flies. So obviously, the population is growing, but they are saying it's growing based on this exponential growth model. So let's create the model. Let's figure out what A and B actually should be here. Now, in this particular case, y represents the number of flies, because y is up here. Down here, the x-axis, that's the number of days. So what I would do is feed this data in as x and y. So the model is y equals a e to the bx, and the only thing you're missing is a and b. So let's see if we can determine what a and b should be. For the first situation, there were 100 flies, y is the number of flies, after 2 days. So in a sense you can, well, instead of b2, we'll make that 2b. So 100 is equal to a raised to the e, or times e raised to the 2b. Still no help here on figuring out A and B. Later on, 4 days, we get 300 flies, so that would be over here. 300 is my y. A is still unknown. B is still unknown, but that's after 4 days. So another equation we could potentially have is 300 is equal to A raised or multiplied by e to the 4b. Well, 2 equations is adequate to determine 2 unknowns. And I think that's probably the best approach here. And how are we going to solve these 2 equations and 2 unknowns? One method is substitution. The problem with solving this equation by itself is there's too many unknowns. 2 unknowns, 1 equation. Can't really do that and find both A and B. However, we could solve for A in terms of B. So wherever you see an A, replace it with 100 over e to the 2b. Okay, let's do that right here. So now this equation becomes 300 is equal to A, well, our new version of A, which is right here, multiplied by e to the 4b. Well, this certainly won't help me find A, but we'll find A later. For now, 300 is equal to 100 times e to the 2b. What did I just do there? I divided these two. You know how to divide when the bases are the same, right? Subtract the bases. Subtract the exponents, I'm sorry. Boy, are we close. Next step, divide by 100. Let's peel away the layers to get to that b. Now, how do we go from here? To finish this problem, I want you to identify the components of your exponential. This is your y. This is really your b for base, not that b, a different b. And this is your circled x for exponent. And you know what we like to do? We love to take exponentials and rewrite them as logarithms. So it's log base b of the old argument y is equal to x for exponent. Because if you remember, the answer for logarithms are exponents. So it should be equal to x for exponent. Well, what do we got here, guys? Log base b. Well, that's log base e. b is e. What's my y? My y is the number 3. What's my x? My x is this whole package up here, 2b. And I think we just found b. So what's b? Well, what's log base e again? That's the natural log, isn't it? Over 2. So I think a quick calculation ought to tell us what b is. And b is going to be the natural log of 3 divided by 2. So let's see. Natural log of 3 divided by 2 is 0.549. 3. So at least we've got one of our variables, b, or one of our constants. They're actually constants. We set those constants to tune it into this very specific problem. So b is 0.5493. Well, what else can we do? Can we get a? The answer is yes. A is right up here. It's 100 over e to the 2b. But we do know b now. So let's get a as well. Now, instead of using that number, I'm going to use the exact version of and see if that helps. So a is equal to 100 divided by e to the 2b. Now, let's see what b is. b is the natural log of 3 over 2. That was the exact version of b. Well, that's interesting. The 2's cancel. And not only that, look where we are with this thing. E is for exponential, natural log for logarithm. They're opposites of each other. That's worth 3 down there. So, what is A? A is 100 divided by 3, which is 33 1/3. So let me express the mathematical model for this particular growth. For this particular research project, y is equal to 100 thirds, or 33 1/3, e to the bx. Now, I think we could use the more exact version of b, which is natural log of 3 over 2. So I'm going to use that. And that way it's more exact. So where's the power in this particular model? The model will help us determine the number of flies at any given day. So let's do this. How many flies do we have on day 2? Let's find out. Y is 100 divided by 3e. Now it's the natural log of 3 divided by 2 multiplied by day 2. Well, that's really nice. Cancel, cancel. And what do we got? Y equals 100 over 3e to the natural log of 3, and it happened again that these canceled. So y equals 100 over 3 just times 3, and there should be 100 flies on day 2. We knew that already, though, because that's how the problem began. How many flies should there be on day 4? Well, if you don't remember, we're about to find out. Let's find out. Y equals 100. We've created a beautiful model of this exponential growth. So day 4 goes in here. We get y equals 100 over 3e to the ln of 3 over 2 times 4. Let's see what we got. 4 over 2 is 2, right? And remember one of our properties of logarithms? We've got so many really cool properties, but one of them is that can we take a constant multiple in front of our logarithm and move it up? We can take any multiple and move it up. It doesn't have to be a constant. So what do we got here? We got e to the ln of 3 squared, which is 9. And there's my cancellation one more time. 900 over 3 is 300 flies. Now, that's not a big surprise because we knew those two quantities. Those, I'm just checking to make sure everything's working here. So what else can we do? We can make a prediction. And here's the prediction I'm about to make. How many flies were there on day 1? 100 thirds e to the ln over 3 divided by 2 times day 1. That's where the x goes. 100 thirds. Now, what I see here, guys, is a 1/2 times an ln of 3. And again, I love that property. You may take anything in front of a logarithm and push it up. And I forgot there's an e there, okay? That gets pushed up, so it becomes 100 over 3, and it's e to the natural log of 3 to the 1/2 is square root of 3. And there it is again, another cancellation. So it's 100 square roots of 3 over 3 equals. And that way, I actually know how many flies we started with. So let's calculate that. 100 times the square root of 3 divided by 3. So 57.735. Well, we can't really have 57.735 flies. So we started with most likely about 58 flies. 58 flies on day 1, 100 flies on day 2, 300 flies on day 4. So now we can really project this out how many flies will we have on day 10? Now remember, the exponential curve really takes off, going this way actually, and so therefore I expect a lot of flies on day 10, and let's finish with that. Day 10, x is 10. So e to the ln 3 over 2, that's the b right there, times x. Well, 10 over 2 is 5. And same trick, we put that up there. Well, it would certainly be nice to know what 3 to the 5th power is. And I'm going to calculate that right now. 3 raised to the 5th power is 243. E and ln cancel each other out. They're opposite operations. So what is y going to be? How many flies are we going to have? A lot. What's 100 times 243 divided by 3? 8,100 flies on day 10. This is by no means linear growth. Linear growth would mean you basically get the same number of extra flies every day, but the longer we wait, the faster this growth process becomes. Now, just so that you can visually see what this is, I'm going to graph this on my graphing computer here, or Desmos as I like to use, which is a website that you can use as well. And what we're going to do is graph y equals, we're going to do the 100 thirds, bear with me here, y equals 100 thirds multiplied by e raised to the ln of 3 divided by 2 times x. Ah, there it is. So we have a nice exponential curve right here. Except it's back here in negative day territory. We don't deal with negative days, right? Negative days don't make sense. So we're going to do some settings here on the graph. The first setting is I don't want to look in the negative direction. Now let's start here at day 0. So I'll change this to x0 if it lets me. And let's go up to day 10. Now, for the number of flies, we don't want negative numbers of flies. And we also know that this peaks at 8,100 because we just figured that out. So if I go to 8,100, that ought to really show me what's going on here. Maybe let's go a little further out here. Instead of 10, we'll go to 12. And then we should be able to see this a little better. Okay, this thing tells the whole story. So on day 8, we're right about here at about 2,700 flies. At day 9, we're up here at about 4,600 flies. And day 10, right up at the peak here, 8,100 flies. So it is pretty powerful to not only create the model, but also to graph it so you can visually see what happened. Okay, now just as we have exponential growth, we have exponential decay. And probably one of the most important problems that we do when we talk about exponential decay is radioactive decay. And radioactive decay is where really what ends up happening is if you started with, let's say, 10 pounds of radioactive material, usually radioactive waste from a nuclear power plant, you would have to wait a certain amount of time, let's say 5,000 years. And then that 10 pounds of radioactive material, only 5 pounds of it would be radioactive. So the 5,000-year period we refer to as the half-life. So now you're down to 5 pounds. Now you wait another 5,000 years, and 5 pounds went down to 2.5 pounds of radioactive material, and then 1.25 pounds, and it just keeps cutting in half and half and half and half. So you got to wait an awful long time before you get a small amount of radioactive material. And that's why they have these big mountains that they basically excavate, and they just put the radioactive material in there because it's going to be dangerous for thousands and thousands of years. So what I'd like to do next, I'd like to model radioactive decay, and the way to do that is to look at exponential decay, which looks something like this. It's actually a very similar curve, except it's backwards, like that. And this is like saying, well, I went from 16 pounds down to 8 pounds, down to 4 pounds, etc. So it's reducing initially by quite a bit, and then it kind of slows down. It's still chopping it in half, but they're smaller quantities, and that's why the curve looks like that. So this is called exponential decay. And the model for exponential decay looks like this. So it's the same thing, except there's a minus in there. We want b to be positive, so we're assured that we get a nice negative coefficient there. Okay. So what I'd like to do is look at radiocarbon dating. Now, for radiocarbon dating, what they do is they take a living organism like us, alive. We have a certain amount of radioactive carbon in our body. We're made mostly of carbon and water. But some of the carbon in your body is not carbon-12, which is the nice, stable version of carbon. Some of it is carbon-14. Carbon-14 is radioactive. I wouldn't say it's highly radioactive, or we wouldn't be here. It's got a half-life of 5,730 years. What that means is that if my body had right now, I don't know how much is in there, but let's say it's a gram. I'm sure it's a lot less than that. But if I had a gram of radioactive carbon, while I'm alive, I'm replenishing my body with more carbon from the environment. And the environment has a small sliver of radioactive carbon. So I will actually maintain that 1 gram for the rest of my life. When the living organism dies, it stops the replacement process. Whatever carbon-14 is in their body is locked in. But carbon-14 is radioactive, and it says every 5,730 years it takes that radioactive material and half of it becomes non-radioactive. So the woolly mammoth had 1 gram of carbon-14 in its entire body, and it died. 5,730 years later, it would only have half a gram. Another 5,730 years, it would have a quarter of a gram. Another 5,730 years, and it would have an eighth of a gram. So you can imagine when we encounter the woolly mammoth and dig it up, all you really have to do is measure how much carbon-14 is in its body and project back to when it had the 1 gram and figure out how long that might be. So the model for carbon-14 dating looks like this. Turns out that the ratio of carbon-14 to carbon-12 is 1 in 10 to the 12th. And that is a 1 with 12 zeros. That's a really tiny amount. So there's no way I have 1 gram in my body. So you would have to take basically your weight or something and divide by 10 to the 12th, which is huge. So we only have a tiny sliver of carbon-14 in a living body. This is the ratio of carbon-14 in living things. Okay. When you end up digging up the woolly mammoth, you notice that you only have 1 part of carbon-14 for every 10 to the, let's say, 14th parts of carbon-12. So you've got a much smaller ratio. The question is, how old is this? Now the model for carbon-14 dating is that the ratio at any given moment can be modeled this way. Now it's decay, so I do expect a minus for my exponent. And you know that there's a B up here, right? And that B for carbon-14 is 1 over 8223. And it's not x, but it's t for time. So let's see if we can figure this out. This is the model. A is given to you. B is given to you. And how do we reconcile this? How do we use this to determine how old something is? First of all, what's the ratio? And the ratio is how many, let's say, molecules of carbon-14 versus, or atoms actually, of carbon-14 versus how many atoms of carbon-12. It's pretty small, 1 to 10 to the 12th. But what's the ratio at time 0, like, you know, right now, while I'm still alive? That's going to be 1 over 10 to the 12th times e to the 0. But e to the 0 is 1. So we do get a very logical conclusion. While we're alive, that is indeed the ratio. But here comes the real question. The real question is this. I just dug up a woolly mammoth, archaeologist, and we noticed that the measured ratio was this. We only found 1 atom of carbon-14 for every 10 to the 13th power, 1 with 13 zeros. That's a lot of carbon-12 down there. So only 1 tiny bit of carbon-14 for all of this extra carbon-12. So that's a much smaller ratio, by a factor of 10 actually, than when it was living. Now, that's all we can do. I mean, when you look at the fossil that you dig up, you say, well, all right, we can measure with instruments how many carbon-14s are in there and how many carbon-12s are in there. That's a pretty accurate measurement. And that will be enough to determine how old this thing was. Now, the model is the following. The ratio you're reading right now is 1 over 10 to the 12th. That's the A. That's built into the model. E to the minus 1 over 8223 times t for time. That's in years. So this is years, and this is the ratio. Well, guess what? We know the ratio of this fossil that we dug up. It is 1 over 10 to the 13th. It's pretty small, which is smaller than when this fossil was actually a living thing. Well, check it out. We can solve for t. It's right there. And how do we get to it? We got a lot of work to do to get rid of these fractions and this e. We need to peel away the layers to get there somehow. First thing I'm going to do is multiply both sides by 10 to the 13th power. That's a 1 with 13 zeros behind it. 10 to the 13th over 10 to the 12th. E to the minus t over 8223. Oh, 10 to the 13th over 10 to the 13th is 1, by the way. But what's this? How do you deal with the bases being the same like that? You squeeze them together and you subtract the exponents. That works pretty well. Don't worry, this number is given to you. It is related to the half-life, 5,730. Now what? Can we make this an exponential equation? Well, we can, but what I'd really like to see, something like this. Nice and clean. I don't want anything in front of my base, like this 10 here. So let's get rid of the 10. Well, I think we have a pretty good exponential equation right now. I'd call this my y, this my b, this my x, and I want you to rewrite it. as a logarithm. The log base b of y equals x. We know these two are interchangeable, right? We've done that in class. So we've got the log base b. Well, today, that's base e of y. That would be right here, 1/10. Equals x. Now, x for exponent is the whole package right there, minus t over 8,223. If this really works, we ought to figure out how old this thing is that had this smaller ratio of carbon-14. We lost carbon-14 due to radioactive decay, so we expected less. We definitely had less by a factor of 10, actually. We all know what log base e is, right? That's just natural log. And I'm really not too thrilled with this minus t. I don't want negative time, so we're hoping that that doesn't happen here. A couple things we can do. Remember the properties of logarithms? Remember that you could break out division and make it subtraction? I think that's going to play a nice role in here because we know the natural log of 1 is 0. In fact, the log base anything of 1 is equal to 0. So that's gone. And here's what we're finally left with. Now, if you multiply both sides by, well, how about minus 8,223? How about minus 8,223? Here's what I get. Cancel with that. Negative, negative is a positive, and we just found out how old this thing is. Now, careful, this has got to be multiplication. Sorry about that. Negative times negative is positive. Good. Positive time is what I want. And I get 8,223 multiplied by the natural log of 10. Now, I don't think I want to do this, but you are allowed to do this. You could pop that up there and make that an exponent. Seems a little ridiculous to do that because that's such a huge number, so I'm not going to do that. I'm going to do it this way. So calculator time, break out the calculator, find that natural log key, and let's figure this thing out. So let's use this version here. 8,223 multiplied by the natural log of 10. Now the natural log of 10 is that number. I'm multiplying that by 8,223, and what do I get? 18,934. So it's a pretty dramatic result because since we do know that radioactive decay matches exponential decay perfectly, and it fits an exponential model, I was able to write down that model. I did provide you with A and B in this case, so you had those, and all you had to do was detect how much radioactive carbon you had in the fossil. Really, a ratio was what we actually detected. How many parts of carbon-14 per carbon-12? Boom, I put the R in on the big side where it said R, and I just solved for T, and out it came. This fossil is 20,000 years old. Now, this can be done with amazing accuracy. So if you ever really wondered, how do they know how old something is? How do they know it's 20,000 or 5,000 or 500 years old or 100,000 years old? How do they know? One way to do it for a living thing is the ratio of carbon-14. Pretty amazing stuff. Okay, the next thing I would like to look at, I've got other models that we like looking at with exponentials and logarithms. And in fact, we haven't really looked at a logarithmic model yet, and that's what I'd like to do. So let's take a look at a logarithmic model. Now, turns out that there are many quantities that use logarithmic models, and earthquakes is one of them. The problem with earthquakes is the following. There are earthquakes that shake the ground by like 10 centimeters. You'll never even feel them. There are earthquakes that shake the ground by 100 centimeters. Then there are earthquakes that shake the ground by, like 1,000,000 centimeters. Those are the ones you're really going to feel, right? So that's going to be pretty dramatic. How do you graph that? So 1,000,000 is right up here. So you say, on day 3 we got one that shook the ground by 1,000,000 centimeters, but what about these 2 days? They're down here. Both of them are down there. It's awfully hard to compare quantities like that when the values are so different. So it was decided that we should be using a logarithmic scale when it comes to earthquakes because of this variability. If we were to take a log base 10, what do we get for the first earthquake? What would you raise 10 to get 10? 1. If you took the log base 10 of the second earthquake, what do you get? That's a magnitude 2. And finally, if you took log base 10 of 1,000,000, what do you get? What would you raise a 10 to get 1,000,000? I'd raise it to the 6th power. Now come over and graph your results. And you would say, well, let's see, day 1, day 2, day 3. On day 1, I had an earthquake that was magnitude 1. On day 2, I had an earthquake that was magnitude 2. And on day 3, 3, 4, 5, 6, I had an earthquake that was magnitude 6. You can clearly see why earthquakes are measured with a logarithmic scale, why we use logarithms. And this is true for earthquakes. This is also true for sound. This is also true for sound because the difference between a whisper and like an explosion is so dramatic in terms of the intensity of the pressure waves in the air that most soft sounds would be way down there sitting on the x-axis, and that explosion would just spike, and you'd never be able to really determine the difference between them. So same thing, we use what's called the decibel scale, dBs, and you might have heard of that when it comes to sound. dBs are logarithms. They're logarithms of the movement or pressure of the air. Now, we have something which is referred to as the Richter scale. And the Richter scale is a logarithm based on intensity. You might have heard of the Richter scale. And R is calculated as the log of an intensity over intensity 0, where intensity 0 is really equal to 1. And basically, that's the minimum intensity it's used for comparison. So I guess the Richter scale is more or less the log of the intensity. And you can think of the intensity as movement of the Earth, like we did earlier. So what we were looking at earlier was the Richter scale. So if you had an earthquake that was 4.0 on the Richter scale, what's the intensity of that earthquake? How much would the ground be moving? Well, the Richter scale reading is 4. This is a logarithm. Log base 10 is what we use for this, and there's my intensity. Well, it's perfectly set up to calculate this intensity because this is x equals log base b of y. Remember, the answer for logarithms are exponents, so we match all that up, and we rewrite it as y equals b to the x. So y is right there. That's the intensity. B is base 10. X is the Richter scale 4. The intensity is 10,000. So that's a relatively big earthquake. But what happens when they report on the news that it went from a 4 to a 6.3? So a 6.3 earthquake. So the Richter scale is the log base 10 of just the intensity. And therefore, 6.3 is the log base 10 of the intensity. And we label it up again. X for exponent, B for base, Y for argument, directly maps into y equals b to the x. Our y is the intensity we seek. B is the base, 6.3. And if you do that calculation, you roughly get about 2 million. So I got to tell you, when you hear that one earthquake was at 4 and one earthquake was a 6, it doesn't sound like a big difference, you know. From a 4 to a 5 to a 6 doesn't sound like a dramatic. I mean, hurricanes have those intensities as well, strength 4, 5, and 6. But when it comes to an earthquake, going from a 4 to a 6 is a big deal. As you can see, the ground only moved 10,000 here. Here it moved 2 million. So just 2 units higher in the Richter scale is just a dramatic increase. A dramatic increase. In fact, going from a 4 to a 6.3, you get a 200 times increase on the intensity of the earthquake. Pretty dramatic increase. So that's something worth noting when you hear those numbers. So if you hear a 7 or an 8, they're really big earthquakes. An 8 to a 9 has got to be devastating, you know, considering that a 6.3 is 2 million on the intensity scale. Now, the last thing I'm going to leave you with is I'm going to talk about Gaussian models. Gaussian models are a little more complicated. They are based on exponentials, but a Gaussian model looks like this. They're a little tougher to deal with because of the model. The exponential model is not as basic as the one we had earlier. It is an exponential model. It does use base e, and this is what it looks like up here. So one issue is that we've got three different variables here, or constants, a, b, and c. Now, what you're going to end up seeing with a Gaussian model, and why we're so interested in it, is because it gives us the bell curve. And the bell curve is a distribution. And we see these kinds of distributions all over the place. Where do we see the distribution? Of course, as teachers, we see them in grades all the time. There are people, a lot of people in the middle, a few people up at the top, and a few people still at the bottom, and it's the way it always is. It's a normal distribution. I've seen in a textbook a wear pattern on a set of stone stairs that were like, 2,000 years old. Now, on the set of stairs, where do most people walk? On average, people are walking around the center, And then a few people are they like to be to the left, and a few folks like to be on the right. And so if you look at the stairs, the stone stairs, you see a dip in the middle where it's worn out. And it's worn out in the shape of a Gaussian curve. A Gaussian curve is a great way to model these real-world distributions. Now, the standard normal distribution looks like this. And luckily, this takes some variability out of the problem. Now, it's hard to get into exactly why there's the square root of 2 pi there, but that is used, that's called a normal distribution for populations. So I'd like to take a look at this example in the book, which models SAT scores. The SAT score model looks something like this. In order to really apply this, you need both A, B, and C for your specific problem. And they've gone ahead and given us all that. So this is for the 2011 SATs, and it's 0.0034 That's my A. My E is right here, minus. Now it's x minus 514 squared over 27,378. So I'm not going to ask you to come up with those numbers necessarily, but I do want you to know what the shape of that curve looks like. So I think maybe this might be a good opportunity to take a look at this graph. So I'm going to turn this off, switch over to the computer, go to Desmos here, my graphing calculator, and let's see what this looks like and see if they really did get an accurate distribution of those SAT scores using this Gaussian model. So y equals 0.0034. We need e raised to this power. Let's see. We've got a minus. What is going on here? Let's get that out of the way. 0.0034 times e raised to the power, and it's minus x minus 514 squared and then that is ended up divided by 27,378. So what on earth does this thing look like? Now I got to come over here and change the scale, and the x is actually SAT scores. So let's put some SAT scores, like from 200 SAT score to 800. And the y is really called the distribution. And the distribution here, I don't think we have to go very high. Actually, it's that 0.034. So let's see what this looks like. I'm not sure why that's not taking. Sorry about that. All right, let me just zoom out here. I'm not sure what's going on. It's not working. Well, I'm not having any luck here, guys. My Desmos here has locked up. Let's see if we can make this work. All right, I think we're in better shape here. Let's see if we can get this in quick. 0.034 e raised to the minus x minus 514. There we go. Squared divided by, divided by 27,378. I just want to see what this looks like. Now, the distribution, again, the x should be SAT scores. Let's make this work this time, 200 to 800. And the y is this thing called distribution. And I'm not sure it has much meaning to us right now, but at least it'll show us our shape. And there it finally is. What you're looking at is a Gaussian. And the Gaussian is a bell curve with a peak. And look at what the peak is. The peak is at x equals 514. And if we split this bell curve in half, half of the students will be over on the right side with a higher than 514, and half of the students will be on the left side with lower than 514. So I don't think we're not going to do too much with the Gaussian. I did want you to see it. It is an E or exponential curve, but it's a very different exponential curve. It doesn't give you exponential growth or decay. It's interesting. It gives us this Gaussian, which is a distribution, usually a distribution of grades or population, and it provides us with the ability to find out what percentile you're in, and the normal distribution, there's other things that are part of this. Sigma, which is a standard deviation, and you might have I don't know if you've ever heard of 6 sigma. And 6 sigma is, sigma is the standard deviation, and 6 sigma would put you way out over here. 6 sigma is really far out on this curve, and companies that have a 6 sigma program They want you to be way over here, and that's their productivity and no accidents and all that kind of thing. They want you to be on the very, very high end of that Gaussian curve. They don't want to be a company that is an average company. They certainly don't want to be on the other side. They want to be way over there at the very top of the curve, closer to the highest possible grade. So that's it. So I would really work with the exponential growth and decay and also look into those logarithmic models and really practice. Look at some of the homework problems. Now, the other thing about next week is that we do have an exam coming up. So I believe it's important for you to take a look at the review problems on the website to prepare for the exam. I also posted the review notes. So as always, when it comes to reviewing, do the review problems on your own and then refer to the review notes which are on the website for help. If you do need any help at all, send me an email. I'll be very responsive to your email to prepare for this exam. So review problems, review notes, take-home assignment, and also email me if you have any questions. And that should adequately get you ready for next week's exam. Thanks very much. I appreciate working with me on watching the video instead of being in class. And again, if you need any help at all, let me know. Thanks so much.